Lecture 2.2 Galilean Relativity. In the last lecture, we saw examples of how one's frame of reference can change the way you see the world. In this lecture, we'll be a little bit more specific with our definitions and develop the equations for the Galilean transformations between one frame of reference and another. A frame of reference consists of a set of coordinate axes and a clock. So, for example, the person on the left who's standing there might have a clock that tells him the time and an origin and axes defining coordinates to measure some event. A person in motion on a motorcycle would have their own clock and their own set of coordinate axes. The first person we say is frame O, where the variables don't have primes on them. The second system we're calling frame O prime, where each of the coordinates x prime, y prime, and z prime have a prime to distinguish them from the first one. An inertial frame of reference is a frame that moves with a constant velocity and is not accelerating. So both of these frames could be inertial frames as long as any velocity that the coordinate system has is moving in a straight line at a constant speed. As we saw in the previous lecture, Galileo proposed the principle of relativity that says that the laws of physics are the same in all inertial frames of reference. So in other words, no experiment can be conducted to determine if an inertial reference frame is in a state of absolute rest or motion. Okay, so let's develop the equations for Galilean relativity. So to make this simple, we're going to make some assumptions. We're going to assume that, again, we have two coordinate frames, O and O prime. So let's say that this guy is measuring frame O, and the woman is measuring frame O prime. At the beginning, at time t equals 0, the coordinate axes are on top of each other, so x prime will equal x, y prime equal y, and z prime will equal z. They're the same coordinate system. As time evolves, we're going to assume that the O prime frame slides along the x-axis with a constant velocity u. So that at time t equals 0, again, the coordinate axes match up, but as time goes along, the x coordinates will be changing due to the sliding of the O prime frame relative to the O frame. Okay, so let's write down the first Galilean transformation equation. And it describes how to calculate coordinates in this moving reference frame given coordinates in the initial frame O. So x prime is going to be the x coordinate of our object, which is the red dot, in this O prime reference frame. So if this is the x-axis, x prime will be this distance from x equal to 0 out to where the object is. So that's x prime. It's equal to the measurement that somebody in the O frame would measure. That's the distance from here all the way out to where the object is. So this total distance, that's x, minus how much the O prime frame has slid compared to the O frame. And so again, so if O prime is moving at a constant speed u, then the distance that O prime will have moved is just going to be the velocity u times the time t. So we see that x prime is just equal to x minus ut. Because we're assuming that all the motion occurs along the x-axis, the y coordinates of the particle and the z components of the particle will be the same in both reference frames. So y prime will be y, z prime will be z. So we can derive a set of velocity transformation equations by just differentiating our original equations. So Vx prime is just going to be the time derivative of x prime. Vy will be the time derivative of x. And u is just the time derivative of u times t. Since u is a constant, the time derivative of ut will just be u. Similarly, vy prime will just be vy, and z prime will just be vz. So the way this looks over here is, imagine that you've got this person in frame O looking at this object moving through space. Frame O will see this object having a velocity vx. Person in O prime will see it have a different velocity, call it vx prime. The relationship between these things is very simple. In fact, vx is just going to be u plus vx prime. So you just add the velocities like that. So if we wanted to figure out what vx prime is, that's vx prime. You just take vx and you subtract the relative motion between the coordinate systems. Because, again, we're assuming that the motion between the coordinate systems is entirely in the x direction, this is why there's no contribution of u to vx or vy. And if we now differentiate this set of velocity transformation equations to get accelerations, we see that the accelerations are exactly the same in both coordinate frames, because u is a constant. So when you differentiate that, it's just going to be 0. Okay, so what we've just described are often called the Galilean transformation equations, which show the measurements in the primed coordinate frame in terms of the measurements in the unprimed frame. If you invert it to solve for x, y, and z in terms of the primes, you get this. So all you do is you move minus ut to the other side of the equation to get x equals x prime plus ut. And similarly, vx is just going to be vx prime plus u. So these are sometimes called the inverse transformations, where these are the Galilean transformations. All right, so let's look at a couple of examples. So let's assume that Olivia drives past Oscar at 60 miles per hour. Olivia estimates that our red sports car passes her at 40 miles per hour. How fast is the sports car moving in Oscar's frame of reference? So you really just add the velocities. So Oscar would see the car going 60 plus 40 or 100 miles per hour. But let's see how to use the transformation equations just to get used to them. So there's Oscar. We're going to assume that Oscar is in the unprimed frame. So in the O frame, Olivia is going to be in the primed frame. So Olivia will be making measurements O prime. So we know that Oscar sees Olivia drive past him at 60 miles per hour. So this information in the problem is telling you information from Oscar's perspective, right? And that's what we need. So remember, it's the O prime frame. So U is going to be the velocity of the O prime frame as measured by the O frame. And that's what we're given in the problem. We're also given that Olivia sees the sports car passing her at 40 miles per hour. So that's from her perspective. Since she's in the prime frame, that means that Vx prime is going to be 40 miles per hour. So if we look at the addition of velocities formula, we're trying to solve for the velocity as seen by Oscar. So Vx equals Vx prime plus u. So Vx is the thing we're trying to find. Vx prime we saw is just 40, u is 60, so 40 plus 60 is 100 as we expected. Very simple math, but easy to get confused with all of the primes and unprimes flying around. It's worth noting that we kind of arbitrarily just assigned Oscar to the unprimed frame and Olivia to the primed frame. We could switch these around and we'll get the exact same answer in the end. So let's do that. So let's let Olivia be the unprimed frame now. And now Oscar is going to be the prime frame, so we've switched them. Let's see how that changes the setup of the equations. So again, the information we were given the problem was from Oscar's perspective. So since Olivia is now in the O frame, we need to know what the velocity of Oscar's frame is relative to her. So if she was moving at 60 miles per hour to the right, relative to Oscar, Oscar will be moving at negative 60 miles per hour relative to Olivia. So again, we're in a frame where Olivia is stationary, so it looks like Oscar is going backwards by 60 miles per hour. So U is going to again be the velocity of the O prime frame relative to O. So now when Olivia measures the velocity of the red car, now she is in the unprime frame, and so now we assign Vx to be 40 miles per hour. And now we're trying to find Vx prime to find out what Oscar sees. So we use a different equation now because we're trying to solve for Vx prime instead of Vx. So Vx prime equals Vx minus U. Vx is 40 miles per hour. U, though, is negative 60. So we have 40 minus a negative 60 is 100 as it should be. So Oscar still sees the red car going 100 miles per hour, but the math is just slightly different when we switch the coordinate, when we switch the frames of reference. All right, let's look at a second example. An airplane is flying at a bearing of 30 degrees north of due east relative to the air around the airplane, and it's moving at a speed of 320 kilometers per hour, again, with respect to the air around the plane. But there's a 65 kilometer per hour wind blowing to the north, and so that velocity has to be added to the velocity of the airplane with respect to the air to figure out what someone on the ground would see. So let's see how to set that up. So here's our compass. North is up, west and east is sideways. We'll let the ground observer be frame O. The frame O prime isn't attached to any particular object. It's not attached to the airplane. It's attached to the air that's moving northward at 65 miles per hour. So if it helps, you could think about following a balloon northward that's being carried by the wind. But this O prime frame is really kind of attached to the air that's moving at a constant velocity north. So since the observer sees the air moving northward at 65 kilometers per hour, our velocity between our coordinate frames will be U 65 kilometers per hour. Okay, so remember that we're always assuming that the motion between our coordinate frames is always going to be along the x-axis. So since the wind is going northward, it means that our O prime frame is moving northward relative to the observer on the ground. So we have to pick our x-axis to be parallel to that motion of the air northward. So x is going to be north. Y we can pick to be either west or east, but let's pick it to be pointing in the east. So those are our coordinate frames. We can now look at what our airplane is doing. So it says that the airplane has got a velocity of 320 kilometers per hour at 30 degrees north of due east, relative to the air. So since the air is, the rest frame of the air is in the primed frame, then this 320 kilometers per hour is going to be V prime. We could figure out the components. Again, it's a little bit funny, right? The Y component is now horizontal. So to figure out the horizontal or the east-west component, we do 320 times cosine 30 to get 277 kilometers per hour. In the north direction, Vx is going to be 160. We use the addition of velocity equation to solve for what we'll solve for what the x component of the velocity is as measured by the ground observer. Remember, somebody on the ground is in the unprimed frame. The airplane measured relative to the air is in the primed frame. So we simply plug in 160 for Vx prime, u was 65 to get a total of 225. And Vy is just the same as Vy prime, so that's just going to be 277. So we can now calculate the speed of the airplane relative to the person on the ground. Square root of Vx squared plus Vy squared, so plug in 225 and 277 here, you get 357 miles per hour. And to figure out this angle, again, it's a little funny because, the opposite side is Vx prime, or is going to be Vx, and the close side is going to be Vy. So you take the arctangent of Vx over Vy to get 39 degrees north of due east. So this is what it looks like. This is what the motion or the heading of the airplane looks like from the frame of reference of the air, from the frame of reference of the person standing on the ground. It looks like this. So they've got a faster northward velocity component because that's the direction of the wind. Okay, that's it for that example. All right, let's look at one more example that has to do with Galilean relativity. So in this case, we have a stream that's flowing down the page with some velocity u. There's a swimmer capable of swimming at speed c in still water. And so the question is going to be, if the swimmer can swim at speed c relative to the still water, but now we have the water is kind of flowing down like this, which is going to be faster? For the swimmer to start at the bank, swim directly across the current to the same point on the opposite bank, and then swim back. We're going to assume the width of the river is L. So how long would it take the swimmer to go from here over there and then back, versus swimming upstream a distance L, that same distance, stopping and then swimming back down to where they started from? So is it faster to cut across and then come back, or to swim against this current but then go with the current when they come back to the original starting spot? And then the final thing we need to do is define our coordinate system. So remembering that u is the velocity of the water frame, of the O prime frame, that has to point in the positive x direction. So we have to have our x axis pointing in the direction of the flow of the water. So x is going to be pointing down the page like that, and then y, we can just have that point left or right, but we'll make it point to the right, so perpendicular to the water. Okay, so let's look at the motion of the swimmer as they swim upstream against the current, so in the negative x direction, from the point of view of someone on the ground. So the velocity of the swimmer relative to someone on the ground is going to be the velocity of the swimmer relative to the water, that's what Vx prime is, plus the velocity of the water itself. So we are saying that the velocity of the water is just u. We said that the velocity of the swimmer is c relative to the water, but again, the person is swimming upstream, so their velocity is going to be in the negative x direction. That's why we have a negative c here. So our first equation is just that the velocity relative to the ground is just the flow speed of the river minus the speed at which the swimmer can swim. That's how fast they're going up current. So they're not going up as fast as they normally would, just because of the flow. The time it takes the swimmer to swim upstream a distance L is going to be that distance L divided by the absolute value of their velocity relative to the ground. So, so notice this quantity Vx is going to turn out to be a negative value, right? Because we're assuming that the flow speed of the water is less than the speed at which the swimmer can swim. Otherwise, they would never get there. So really what we care about is you have to take the absolute value of this to get the time. Otherwise, you'll get a negative number. So take the absolute value of u minus c. That's going to be c minus u, because again, remember, c is greater than u. So this will be a positive number. So now when the swimmer turns around and goes back downstream, we get the same equation, but now the swimmer is swimming in the positive x direction, so we have a plus c instead of a negative c. So the time to go downstream is now going to be L over c plus u. So the total round trip time is just going to be adding those two values together. So L over c minus u plus L over c plus u. Get everything over a common denominator. The u will cancel a negative u there. You'll get a 2c up top. And this is the, you can write this as the sum of two squares in the bottom. Divide top and bottom by c. You can simplify this expression to 2L over c times the quantity of 1 over 1 minus u squared c squared. So that's just a couple of steps in there to simplify. I recommend you go through it on your own to convince yourself you get that answer. Okay, so that's how long it takes the swimmer to go from here upstream and then back down. Notice that this term right here, when the flow speed of the river u goes to 0, this term goes to 1. And so 2L over c, that's just how long the swimmer would take if they were in a lake. So if there was no flow of the river at all, u would be 0. The amount of time it would take to go up and then back is just going to be the total distance, 2L, divided by the rate at which the swimmer can swim. So 2L over c. This extra term has a correction for the fact that you're swimming against the current and then with the current. All right, let's now calculate the second part. So let's see how long it takes the swimmer to go from one bank to go straight across, turn around, and then come back. Okay, in the ground frame, that is the frame of reference attached to the two sides of the river, the person just wants to swim straight across, and so the x component of their velocity vector is going to be 0, right? Because x is along the river. They're not going to be drifting down or drifting up. They've got to correct their swimming so that they go in a straight line straight across. So in the ground frame, we want Vx to be 0, and so just the velocity is going to be whatever their y velocity component is. Now, if that's true of the ground frame, what they have to be doing in the water is they have to be fighting the current so that they don't get pulled downstream. So there's got to, in the frame of the water that the swimmer is swimming in, there's got to be a component that this Vx prime has got to be a negative component here pointing upstream, because basically this vector plus the water velocity vector, the sum of these two has to add up to this vector that's straight across the river. So, in other words, if you look at, so Vx prime, the transformation equations, Vx prime is going to be Vx minus u. We've just said that Vx is equal to 0. That was 0 right there. So Vx prime is just equal to minus u. In other words, Vx prime, this component of their velocity in the water, it just has to equal the velocity of the current going downstream. So this just says that that component is equal to negative that component. So we know that, I guess I should have said this, that the total speed of the swimmer through the water, we know that is just equal to c. That's a constant. So that's going to be the length of the diagonal. The length of this velocity vector is going to be the total speed of the person swimming through the water, and we are assuming that that's a fixed value equal to c. So we know that's c. We know this component here is u, or negative u. And so if you plug in the Pythagorean theorem, we can solve for what the horizontal component of their velocity vector must be. So, again, because of the transformation equations, we know Vy is the same as Vy prime, which is just going to be the square root of c squared minus u squared. So, the time to swim across and back only depends on Vy, only depends on the component of their velocity that's going directly across the river. So the time to go across and then back is going to be 2L. That's the total distance, L across and then L back. And then the velocity is going to be this Vy, which is that square root of c squared minus u squared. We can make this look like the term from the previous result. So we can factor out a 2L out in front, divide top and bottom by 1 over c. So we get 2L over c times the quantity of 1 over the square root of 1 minus u squared c squared. Again, convince yourself if that's not self-evident. Okay, so now we can compare the results. The time to swim upstream and then back down again, we'll call this t parallel, because you're swimming parallel to the motion of the river. It's going to be 2L over c times this factor. Time to swim across and back, 2L over c times this. You get there's a square root term in the denominator. Other than that, everything is the same. So which is bigger? Well, you can kind of look at this and, since u is always greater than c, this thing in the bottom is always going to be less than 1, so you can figure it out. The other thing you could do is plug in some numbers and see which one is bigger. So let's suppose that the width of our river is 50 meters. Suppose you could swim at 1.5 meters per second. That's about 3 miles per hour, which is actually pretty fast. And we're going to assume that the flow of the river is about 1 meter per second. So if you take all of these values, plug them in to our two equations, we see that the time it takes to swim upstream and then back is 2 minutes exactly. And then to go perpendicular is 89 seconds, or about 1.5 minutes. So it's quite a bit faster to swim across the river and then back than it is to swim against the current and then swim back down. So this is the faster one. So the reason we spent so much time on this river example is because we can transfer the results of this simple example directly over to interpret a very famous experiment called the Michelson-Morley experiment that has profound implications for special relativity. So anyway, remember this result because we're going to use it here in a couple of lectures for special relativity. Okay, that's it.